So it's my pleasure to introduce a former colleague, PhD student. We were together at INRIA, and he's now working at Harvard Medical School in the Surgical Planning Lab on deformation-aware augmented reality for neurosurgery. Nazim, it's your turn.
Okay, thank you, Hugo, for the introduction, and thank you for the opportunity to present my work. I'm actually very happy to be here to see, at least to talk with people, former teams and everything. So yeah, so I'm a postdoc right now at the Brigham and Women's Hospital and Harvard Medical School. So they have this lab, part of the radiology department, called the Surgical Planning Lab. So this work was also collaboration with guys from MIT and INRIA with Stéphane Cotin. So it's about brain surgery. So I'm part of a neurosurgery team, and it's a tool to be able to provide augmented reality for such procedures. So I will start by describing the actual surgery. So craniotomy is one of the main surgery used to remove tumors from brains. So it follows certain pipelines. So from MRI scans, surgeons identify the tumors and identify a way to access the tumor. So they try to choose it so it best access the tumor, and it could be the smallest possible, so patient exposure is minimized. So to access the brain, they remove a part of the skull, like you can see in the image in the middle here. Once it's done, you have this microscopic view. So this is the actual view on the right that they do see, and they try to access the tumor going through the parenchyma while avoiding vessels and risky areas. So the problem with this surgery, although it's a very known problem, and I think Alex is here, he can talk better about it. So it's the brain shift. So the brain shift, it's a deformation of the brain that occurs due to gravity and due to loss of CSF, liquid fluid, and other phenomena, which makes the preoperative planning, the MRI, is not longer valid. So you can see on the image this kind of brain shift that will shift one or maybe sometimes both lobes. And the access to tumors is more challenging because we need an updated neuronavigation and updated images that will translate this brain shift. So there's plenty of existing approaches, and this is a subject that has been around for like 20 years or something. There's like 3 families. The first one is like to add more imaging, like intraoperative ultrasound, intraoperative MRI. We have also augmented reality, which is the way I'm going to take, and also preoperative planning, also the work of Alex Bilge and the former team Mimesis and before Chakra and everything. So using mainly SOFA, you can find more information on it on the websites. So our goal, to summarize, is to have this kind of visualization. So what you see is in blue the new surrounded by purple, it's the new position of the tumor, and the dotted blue is where the tumor was before. So we want to compute the brain shift, and we want to do a new visualization to append to overlay on the surgical microscope. So what makes our approach different from others is that we want to use the less hardware possible. So we just want to rely on imaging coming from the surgical microscope. And we also want to use only one monocular single image. It makes it more challenging, but at the same time, we avoid any difficult calibration and tedious setup. So our solution was to align this, following this scheme is to align preoperative vessels using a little bit of deformation with intraoperative vessels that we can segment. So we have this image here where we can extract the vessels using deep learning, and we have the preoperative vessels that you can build upon FEM model, and we can align them both. So it permits to do a 3D, 2D registration in a way that with the physics, we can compute the 3D that is missing from the image. So, but before that, we need to process the intraoperative images. So what we do want is to have a segmentation of the cortical brain vessels. So cortical brain vessels are the vessels occurring at the surface. So we use deep neural network because it seems like most efficient way to do it. Other approach exists, but we wanted to try something robust because this is the only information we have intraoperatively. The problem is that we had only 10 images. And with 10 images, you don't go far using a deep neural network. And I agree with Eleanor that having data is maybe half the work when you use deep neural network. So what we're trying to do is to create more images from only 10 ones. So we use neural style transfer. So neural style transfer is a very funny way to add style to an existing image. So you can see here a photo of Hugo. This is the style. And with this kind of method, you can have this stylish Hugo that we all want to see one day. And this method could be applied to our case. With a little bit of modification, we could have this this nice new image at the right coming from the first image in the left. So we have these three inputs: the left image, the mask of the actual image, and one mask randomly generated. And with this, we can have a new image and then extend our database of images. So okay, so yeah, so the question now is how to have these small images that can be automatically generated. So there's plenty of ways, and I decided to use SOFA because I was at ease with it. So basically, I just use the basic component of SOFA, like loading vessels and projecting them and create this kind of mask. So it's a very nice tool if you hack it to use also to generate new image for your to feed your deep learning algorithm. So we went from 10 to almost 2,000 labeled image, and labeled is an important keyword here because we don't have to label them manually, just have to project them and to tweak them with a little bit of image processing, and it was done. So with this, we fit everything to CNN. We followed the classic unit architecture. So basically, it tries to classify the pixels, saying it's a vessel or not. We used a weighted cross loss entropy because we have unbalanced data. You can see that the background is more present than the foreground. I don't see myself. Do you see my? Is my camera off?
Yeah, your camera turned off, I think. But I mean, you can return it on if you can, but otherwise the presentation works perfectly fine.
Okay.
Good.
All right. So yeah, so we went to this using this unbalanced cross entropy to be sure that we do have a correct segmentation and correct loss, not to overfit the background but the vessels. Now going to the 3D part, which will be less more straightforward. So from the MRI, we can segment the vessels. One important thing that we don't need all the brain. We just want one little bit, one spot that is going to be the craniotomy. And then we can generate skeleton here. So there is a plugin muscularization using in SOFA using Seagull that does the job. Other method also work on MRI. I choose to work with this. With no particular reason. So once we have this, I also used a beam model. I think it's the beam model day to day. I don't know. It seems like trendy again. But yeah, nothing particular here. Just wanted to have almost articulated model that can help me get the out of plane deformation. So when we put all together, we have this fine equation that we try to do this registration by minimizing the distance between what we have undeformed and what's deformed. So before that, there is an initial step that I will skip to have everything in one point of view. But what we want to do, because it's only 2D, we want to have the sight lines you can see here coming from the camera to the mesh, using the FEM as constraint. I will go fast on it because I'll have less than a minute. So yeah, so for data processing, I use the usual suspect like 2D slicers, Seagull, SOFA, and Keras. We tried this on 6 cases. I don't have a video, but you can see the overlay here, and the final result. You can also see the branch shift deformation on color in the 3D. You can see here the 3 cases. We do have another small addition, which we try to have not only the cortical vessels because the surgeon already see it, but we wanted to map it with the tumor. So again, what's important, they don't really care about the full brain. They just want to see exactly what's inside in this particular zone. So pure geometric mapping was enough, although more are present. So I think it's one of the last slides. We can see here some accuracy of the registration. So it's mostly simulation, and we try to measure the compensation. So how we can compensate for brain shift. In this, you can see the higher the better. So we can see at the level 0, which is the cortical vessel, we can reach up to 80% of compensation. But when we go deep, even if you have a biomechanical model, the compensation is lower, but it's still good with more than 20%. And accordingly, we can see the TRE error between the ground truth and the measurement. All right, so to conclude, this is work that has been done like some earlier this year. It was really amazing to work with those data and to show that we can have a brain shift aware augmented reality using only one image. They have a very nice setup here called Amigo. It's an operating room, and I hope we can try it as soon as we can go back to hospital. We can reach low TRE and good compensation. And obviously, everything is sensitive to cortical vessel segmentation that could be improved, and it's actually been done. And that's pretty much it. So thank you, everyone, and sorry for the overrun.
Thank you very much, Nazim, for this presentation that has been awarded by François as the best presentation award already. So yeah, thank you for the presentation. Is there any question for Nazim? I see already one from Vera, who is asking DNN and convolutional network or neural network at best are 70% accurate. Is that enough for medical work?
It depends of what you say by medical work. It's better than what we used to have, especially in this case. There's only one work that tries to deal with segmenting cortical vessels, and it was like very hand engineered work. But I agree with you that it's not the best, but it's not accurate enough. I don't know, but it's still the best right now. Although I will not say that 2000 image is very low. It was just to start to play with. So with more image, I think we'll have more results, obviously.
So Nazim,
yep.
It was a pleasure to see you today.
Yeah, I don't see you, but
yeah, I want to see my face. Maybe okay. I can authorize the camera. I had a question for you for the minimization you show.
Yep.
You seems to minimize on all the nodes. Is it like DU are all the nodes, or yep. What are the variables that you minimize in the minimization?
So here I have you see here P is the camera projection. So this in 2D.
So I see that the cost function, but what variable you change?
So I minimize the distance between points on the central line of the image and nodes on the beams. But these are manually selected, not manually. So
can you put some force or?
Yes, I put here small force on both. This small case, what generates forces. So it's just an elastic force. It's very similar to what we did with the liver. If this is.
Yeah. Is it like, because so as we always discuss, I think we already discussed that before, but these are forces that do not exist in reality.
Yes, they do not exist. Yeah.
And would it be possible to use something more physically based? I mean.
I think the way I did it is maybe not the right way, because there's a prescripted displacement. With displacement will be more. I didn't have to compute forces, but at the end, because I prescribed displacement and because deformation is not that big at the surface, I could actually skip the physical model.
Okay.
I could use something like as rigid as possible model or something, or maybe
really?
articulate way. Yeah. So
Okay.
yeah, so I'm thinking about maybe less physics on this part, but
Yeah, okay. Thank you.
Thank you. Nice to see you.
I see. Maybe we can take this very last question from Francois. I have a question regarding the mechanical model of the vessel. How did you handle the branching, on the beams to mimic the tree like?
Some specific position orientation. What do you mean by branching? Like when the
No, yeah, because you have the beam which is this way. I won't make it this way, and suddenly you have a branch which is starting this way. How do you handle the difference of orientation?
I actually didn't handle it at all. I try to position. I do take the branching point, but I try to have like no more than 20 to 30 points. But I didn't handle it because I didn't cause any problem. I don't know if it caused problems with something you used before.
I see. I think it's also the question of how actually both lines, both beam path are actually constraints one to another. But yeah, we're gonna have I was gonna say we're gonna have some time to discuss that, but actually this very last session is gonna be without a break at the end, so that we do not end too late. But
yeah, thank you very much.
And do not hesitate again to contact Nazim either right now in the private chat, because I guess Nazim will stay a bit with us. And otherwise, if you want to get the contact of Nazim, was that on your last slide, Nazim, as well?
Yeah, but my name is I mean, it's not that common.
Okay.
So yeah.
Mr. Haouchine, so you can find the guy.
Thank you very much.
Thank you, Nazim.
Bye bye.